On chapter 19. Remember, this is the second part of 19. We've already done the first part. So this is basically part 2, and we'll go through it. There will be some problems in here that I'm going to tell you to look at but ignore, and we'll go through that as we go. All right, remember we're starting at section 19.5, review, first law of thermodynamics. Law of conservation of energy. Energy can neither be created nor destroyed. It can only be converted from one form to another. Second law, that was the one that involved directionality. For a spontaneous reaction, the entropy of the universe must increase. Remember, entropy is the disorder. We'll go back through that again in a little bit. Third law, and this is the one we're going to really use the least. It's kind of like a placer law. The entropy of a pure crystalline substance at absolute zero, K is 0. Now, the really interesting thing about this is if you try to research it, in theory, a group made it to absolute zero and things were not what they appeared. But nobody's ever been able to reproduce it, even the group who did it, so they're still working on it. Okay, now we're going to talk about standard states. Standard states for thermodynamics are measured as 25 degrees C. Solutions are 1 molar, gases are 1 bar, or pretty much 1 atmosphere. This is similar to STP in gas laws, but these are the thermodynamics, and it's designated by putting the little degree symbol. So that is standard. So delta S, standard, as long as you've got the degree, it's standard. Okay? And they are in Appendix 2 if you were to need them. Okay, now let's do a review here and keeping in line with my colors. Okay, enthalpy on this one is, for spontaneity, is exothermic. It's non-spontaneous if it's endothermic. That means that the value is negative. And delta H is less than 0. Entropy, on the other hand, it has to, for spontaneity, has to increase. So the value has to be positive. So what we're saying is got to be greater than 0. Okay? Now, if you'll remember back in chapter 5, I think, and 12:12 for this text, we did delta H of reaction using the products minus the reactants. We use the moles, etc. You can do the exact same thing with delta S. The values are in Appendix 2. I believe there are a couple of these in mastering. I'm not going to do any on the test. So for this one, not on test. Not on test. Etc. Before we get started, again, remember, this is all part of the test for the 5th test, Part A, which will be next Friday, or this Friday, whichever time you're looking at it, the 17th. I believe it's the 17th. Anyway, that's the Friday where we'll cover this part. Okay, so the question is that, is a reaction spontaneous? Remember, spontaneity means that it'll proceed on its own without any outside interference. Okay? So we can have conditions like this where delta H is less than 0, so it's saying go. And here delta S is less than 0, so it's saying no. Okay, in the next case, we have delta H greater than 0, which says no. So according to the enthalpy, it says no. But here, delta S is positive, so it says go. So in some cases, you don't really have a choice if both say go, then it's automatically spontaneous, always. If both say no, then it is non-spontaneous. The problem is when you have these two cases where one says go and one says no, who wins? Well, that brings us to the combination. Before we get to that, there's one other thing we have to know. We have to realize that delta S is related to temperature. Okay? So, we have a temperature component in the process. Okay? Now, these two equations I'm not going to have you work anything with, but we're going to need them when we get to this part, because what we can do is combine them into one equation, which is called the Gibbs free energy, after J. Willard Gibbs, who was one of the first Americans to win the Nobel Prize. And what he was able to do is combine enthalpy with entropy and determine spontaneity. This is the equation you need to know. These are basically the same thing. This one is standard. Okay? The first one's non-standard. We'll get to non-standard when we get to electrochemistry, but for right now, we're going to use the standard one. And so what it does is it allows us to combine enthalpy and entropy plus the temperature consideration and determine whether a process is spontaneous or not. Okay? So, spontaneous reactions are delta G greater than, no, that was wrong. Let's look at that. Less than 0. Delta G basically follows delta H, which is opposite of delta S. So non-spontaneous reactions then are greater than 0. So they're positive. Okay? Now, equilibrium reactions are when delta G is equal to 0. And we will work with this, but we'll do this later. So if we look at spontaneity, we can combine enthalpy and entropy into the term free energy. Okay? Again, free energy is when delta G is less than 0, so it's negative. Okay, and there's terminology associated with this. It is similar to the enthalpy, but it's not quite. So we said something was endothermic if the enthalpy of the reaction decreases. But with free energy, we call it endergonic. Okay, so if it's endergonic and it's decreasing, it is a non-spontaneous or unfavorable reaction. Okay, delta G is greater than 0, so it is positive. Now, if energy is given off, and this is the free energy, so it's delta G, it's called exergonic. So basically what you're differentiating is endothermic is enthalpy. Endergonic is free energy. Same thing with exothermic and exergonic. And then for those of you who go on to take organic, they do endergonic and exergonic. Okay? So in exergonic, the free energy of the reaction process increases. That means it's spontaneous or favorable. But delta G is less than 0, so it's negative. And my little parentheses screwed up here. That was supposed to be negative in parentheses. Okay? So, remember, delta G are similar but different. Okay? Now, when you look at free energy, what happens is if you're looking at a reaction and we're looking at spontaneity, At equilibrium, that's the lowest value where delta G is equal to 0. Okay. If it's on either side, again, positive or negative, then it's spontaneous. So you can look at this graphically, and it's really not bad to do so, but we'll look at another graph in a little bit. So let's revisit spontaneity. Enthalpy is spontaneous when it's exothermic. It's negative. So delta H is less than 0. In entropy, it's going to increase. So we need it positive to be spontaneous. So it's greater than 0. Okay, this is free energy is exergonic. Again, it'll be negative. So the value is less than 0. Okay. All right. So the question is how do we work the problem? Okay. Let me double check something. All right. I don't have it here. Okay. On the previous slide, we had the formula delta G standard is equal to delta H standard minus T delta S standard. Okay. Now, also on the slide, no, it's the next slide, sorry. The temperature must be in Kelvin. So remember, Kelvin is equal to 273.15 plus C. Okay? So when we set this up, if we read it, delta H is given, delta S is given. What is delta G for the reaction? Is it spontaneous? So that's the first question. And the other question is if it's not, calculate the minimum temperature. If it is, or if it's not, calculate when it becomes spontaneous. If it is, calculate when it becomes non-spontaneous. Okay, so one thing that we have to look at is, wait a minute, we got kilojoules per moles here and we got joules per moles here. So one of these has to give. So we either use, have to use the same units. So it's either going to be kilojoules or joules. I'm going to use joules. The other thing up here is I'm going to do this in Kelvin. So my Kelvin is 293.15. All right, so when we go to plug it in, I'm going to come back over here and say delta G sub 0 is equal to, and I'm going to do this in joules. You could do it all in kilojoules, it doesn't matter. 4900 joules per mole. And remember, kilojoules are smaller than joules. Minus our temperature in Kelvin, 293.15, times our delta S, which is 83.7 joules per mole K. So this is K. So basically we've got joules per mole. So it's 4090 joules per mole minus 2436.655 joules per mole, which is 163.345 joules per mole as my answer. Or if you did it in kilojoules, it would have come out to be 16.3633 kilojoules per mole, which is fine. So it is non-spontaneous because delta G is positive. Okay. That being the case, we need to know when it switches. Okay, it's like the Q's we did before. It's going to switch when delta G, we need it to be spontaneous, so it's delta G has to be greater, oh, excuse me, doing this backwards, less than 0. Okay, now the easiest way to actually do it is set delta G equal to 0. That's still non-spontaneous, that's at equilibrium, but we can look at it as a value and you go the opposite direction. Either one, for simplicity's sake, I'm going to put this one here. So we need, let me think a second so I don't screw this up. We need delta G, this value here on the other side. Whoops. If it's positive, it's non. So we need the value on the other side to be less than 0. So we have the 40900 joules per mole minus, and the question is the temperature here, so 83.7 joules per mole K. So what ends up happening is we end up with 40900 joules per mole. Have got to be greater than negative T 83. Actually, let's do that the other way, because then we don't have to divide by a negative and flip it. Okay, so let's put the T on the other side. So we have 83.7. I can't even read my own writing. Joules per mole K times T will be greater than 40900 joules per mole. So temperature has to be greater than, let's do this, 40900 divided by 83.7. Has to be 488.6499 K. Okay, so at the temperature we were at before 20, it was non-spontaneous. So once we get above this temperature, and if we wanted to know what it is in Celsius, degrees C, we would subtract 273.15, so it's 215.50 degrees C to become spontaneous. It starts non-spontaneous because it's positive. So it'll become negative when you get above 215.5 degrees C or 488.65 K. Now, on this one, it doesn't matter whether you have Kelvin or degree C. I'm going to ask for one, and if I don't specify, you can give me either one. It doesn't matter. All right. So the next ones we're going to do are going to be more discussion, and I'm going to pause and do those in just a minute.